Let's finish out our study of quadratic equations by looking at a couple of applications. The first one involves the very famous Pythagorean theorem. The length of a rectangle is 1 inch less than twice the width. If the diagonal is 2 inches more than the length, find the dimensions of the rectangle. So we have a little puzzle to solve here. First of all, we have a rectangle, so I'm going to draw a picture of it. And remember, a rectangle is described by its dimensions. It's got length and it's got width. So let's suppose this side is the length and this side is the width. We'll call it L and W. It says the length of a rectangle is 1 inch less than twice the width. Let's translate that English statement into mathematics. It says the length, remember we're calling that L, of a rectangle is can be translated as equals 1 inch less than twice the width. So I'm going to start with twice the width, that's 2 times W, and take off an inch. That's 1 inch less than twice the width. So we have this equation, the length is equal to 2 times W minus 1. Now, we have another aspect to consider here. It says the diagonal is 2 inches more than the length. So let's take a look at the diagonal of this rectangle. The diagonal, we'll call it D, and we can translate this into math as well. The diagonal D is means equals 2 inches more than. 2 inches more than translates into 2 plus the length, L. Now, if I have all of these clues, we want to find the dimensions of the rectangle. That is, what is the length, what is the width? Well, if you notice here, the diagonal divides that rectangle into 2 right triangles. And when we have a right triangle, Pythagorean theorem applies. So as a reminder, your right triangle has 2 legs. We call those legs A and B, and it has a hypotenuse opposite the right angle. We call that C. So in the case of a right triangle, it's always going to be true that A squared plus B squared is equal to C squared. So we can apply this principle to the right triangle that we see on our rectangle up here. So we're going to use Pythagorean theorem as our model. Now notice we have the horizontal segment of our right triangle in terms of W. We have the vertical also in terms of W, but our diagonal here is in terms of L. So let's work on writing that in terms of W. So our diagonal is 2 inches more than the length. But as we can see here, our length is 2W minus 1. So I'm going to replace L with its value, 2W minus 1. So we can rewrite our diagonal in terms of W, 2W plus 1. So now I've got all 3 aspects of that right triangle in terms of W. So again, our model is the Pythagorean theorem, A squared plus B squared equals C squared. But in this case, our A is the horizontal segment, we called that W. Our B is the length, we called that 2W minus 1. And C is the diagonal, 2W plus 1 quantity squared. So that's a quadratic equation. Let's go ahead and execute those exponents with FOIL. So we have W squared plus 2W minus 1 times 2W minus 1. We can FOIL that out. 2W plus 1 times 2W plus 1. We can FOIL that out as well. So we have W squared plus 4W squared. Notice our outside terms here are minus 2W. The inside terms are minus 2W. Those combine to give us minus 4W. And the product of our last terms is 1. Similarly, over here on the right side, we have 4W squared. Outside and inside terms combine to give us 4W. And last is 1. So combining like terms over there on the left side, we have W squared plus 4W squared. We can call that 5W squared minus 4W plus 1. And on the right side, 4w squared plus 4w plus 1. So let's move all of our terms to the left side. If we do that, we can solve it either by factoring or by the quadratic formula. Both of those require us to move everything to one side equal to 0. So I'm going to subtract 4w squared from both sides, lining up like terms. I'm going to subtract 4w from both sides, again, lining up like terms. And we'll subtract 1 from both sides. So that's going to cancel on the right side, and it's also going to cancel on the left side. So we end up with 5w squared minus 4w squared, that's w squared. Negative 4w minus 4w is negative 8w. And the only thing that's left over there on the right side is 0. So we can solve this by factoring out our greatest common factor. So if we factor out a w, that leaves behind w minus 8 equals 0. Setting each factor equal to 0, our two solutions are w equals 0 and w minus 8 equals 0, which gives me w equals 8. Now let's consider that first solution, w equals 0. Remember, that represents the width of the rectangle. If the width is 0, we have just annihilated our rectangle. So even though 0 is a solution to our quadratic equation, it's not a feasible solution for our real-life application. So the only answer that we should consider here is w equal to 8. So we can now answer the question. The width of the rectangle is 8 inches, and the length, well, remember, the length is twice the width minus 1. If the width is 8, we have 2 times 16, which is 32, minus 1, and that gives me 31. Cut. Three, 2, 1. The width is 8 inches, and the length, well, to find the length, we can go back to this expression. Length is 2 times w minus 1. If the width is 8, we have 2 times 8 minus 1, or 16 minus 1, which gives us 15 inches for the length. For our last example, we'll consider a very famous application of quadratic equations. This is an enrichment example. This applies to nature, art, music, architecture. This is found in so many different places. Once you're aware of it, you'll start to see it everywhere. We're going to start with a really simple situation. I'm going to take a line segment. You can see that constructed there on your notes, and divide it in such a way. So I've got my line segment here, and I'm going to find a point to divide it. Okay? We're going to divide it in such a way so that the ratio of the larger piece to the smaller piece. So the larger piece is x and the smaller piece is 1. We're going to form that ratio, larger piece to smaller piece. So that ratio is equal to the ratio of the whole segment. Notice the length of the whole segment would be x plus 1 to the larger piece. So there's the whole segment to the larger piece. So I want to divide this segment so that those ratios are equal. Solve this equation for x. Well, to solve this equation for x, we're going to start by cross multiplying. So we get x times x, which is x squared, and 1 times x plus 1, which is x plus 1. If I move both of these terms to the other side so that it's equal to 0, we could certainly solve that with our quadratic formula. Now, from example 4a, in the previous video, we already solved this. We found out x is equal to 1 plus or minus the square root of 5 over 2. In particular, the positive solution, 1 plus the square root of 5 over 2, is what we call the golden ratio. And the symbol for the golden ratio is this Greek letter phi. This is the golden ratio. That is, if I divide the segment in such a way so that those ratios are equal, we end up with this value, which is very aesthetically pleasing. This positive solution, the golden ratio, gives rise to what we call golden rectangles. So if you look down here at our diagrams, you can see on this side we have a segment divided according to this golden ratio, and if I translate that into a rectangle, we call that a golden rectangle. Within that golden rectangle, you can see this spiral beginning to develop, and we call that the golden spiral. This is found in nature. You can see the picture of the broccoli, the shell, the galaxy, the hurricane. You can see it in sunflowers. You can see it in pineapples. Once you're aware of that, again, you can see it in many different places. A lot of artists will use this proportion in their art and architecture as well. So it's worth it to Google golden ratio, golden mean, golden segment, golden rectangle, golden spiral. It's really fascinating. All of this arising from a very basic quadratic equation.